Yeah, hello everyone. Let us discuss now how do we convert this IEEE standard format into double precision. Okay, the previous lecture we have seen this IEEE 754 standard. So we have seen for this standard we have seen for single precision. Okay, now it is done. Now let us see how do we do it in double precision. Okay, before that let us quickly see the difference between single precision and double precision. So single precision sign bit is let us say sign bit here, exponent bit and mat is apart. So sign bit is 1 here, sign bit is 1, exponent bit is 8 bit, whereas for this one the exponent bit is 11 bits and mantis part is 23 bits and here it is 52 bits. So this way it is different. So on total if you add them, if you add all these numbers, it is going to be 32. If you add all these numbers here, it's going to be 64. But altogether, it is 32 bit, and this one is 64 bit. Okay, so let us begin with here. All right, so let us start now. The number. Let us take the same example what we discussed in the previous session. So it is 85.125. This is the number what we have in your decimal part. Now we need to convert that to its equivalent IEEE 754 format in double precision. Okay, it will be very simple to do it. So as we discussed earlier, we have three-step format. Step one is to convert it to binary. Okay, and step two is to normalize. Okay, and step three is to represent it. So represent what? Represent sign of it, represent the exponent of it, represent the matrix of it. So simple as that, right? So let us do the first step. So first step, representation of that number in binary. Okay, so how to represent that corresponding number into binary? So 85, we know that 85 equivalent binary is what? 1010101. Okay, as I told in the previous lecture, you can able to find that easily by using 84214. If not, you can able to repeatedly divide this by 2. You can able to convert it to its equivalent binary number. As we have discussed already, I am not telling you. If you have any doubt, you can just go through that process. And similarly, this 0.125, if you multiply this by 2 continuously, what value we got? 001. So this is what we got. These are the equivalent binary values. Altogether, 85.125 is the value what you have taken. Equivalent binary value will be 1010101.001. So this was in decimal. Let us say this was in binary. This is the first step. So first step is very much clear and there's no confusion here. Whatever number has been given to you, you try to convert that corresponding number into its equivalent binary. So that's the first step. That is done. Okay. Now let us do the second step. So second step is called normalization. So this corresponding number we need to normalize it, which means we make sure that you represent that as 1.0101001001, which means you count how many values you have moved towards the left side. So it is 1, it is 2, it is 3, 4 here, 5 and 6. So 6 values we have moved, so multiply this by 2 power 6. This is called as normalization. Okay, if you have, say for example, if you have 2 more ones here, okay, if you want to put a decimal point in this place, it will become 7. So 2 power 7 it will become. So that way it is. Okay, so it's called normalization. We have did simple normalization technique we followed. So this is your second step. Second step is normalization. So until here the values will not change in single or double precision. Whatever precision values you take, either it's single or it's double, is not going to make any difference. All right, now let us go into the double precision format. Okay, how do we represent this corresponding numbers in double precision? So we need to represent the sign bit, we need to represent the exponent, and we need to represent the matrix. Okay, so we are trying to do this conversion in double precision. Okay, In this double precision, as we have seen here, this biased exponent value, which is 1023. Okay, so it's like I'll just give you a formula. E dash will be equals to E plus this bias. Say for example, this 6 is the bias here. This exponent value is 1023 plus the bias value is 6. So E dash value, what we got here is 1023 plus 6. It will be equals to 1029. Okay, so this is the first step in the third one. So we are representing this exponent part. So how to represent exponent part? E dash equals to E plus bias. Exponent value will be 1023 for double precision as we discussed earlier, and the bias part what we got here in the normalization, that we are representing here. So we're able to get the E dash. Now one more step here is how to represent this in binary. We need to represent this in binary. The equivalent value of 1029, we know it, we have already seen that. It is 1 0, it's 1 0 1 0 0 0 0 0 0 0 1 0 1. So how is that? I'll just explain you. You can just observe this carefully. So if you look at this one, so what we had here is like 8421 code. We can use it. Okay, same. So it's like 8421. It is 16. It is 32, 64, then 128, 256, and this is 512, and this is 1024. Okay, if you want to get this 1029, we need to add this 1024 along with 4 and 1. Add this 1024, 4 and 1. So it's going to be 9, 2, 0, 1, 1029. So this way we can easily represent the number in binary. So what we represented here is correct. Okay, all right. So this is done. Next is what is the normalized mantissa here? So look at this. What is the normalized mantissa value? So this corresponding number is your normalized mantissa. This is called as what? Normalized mantissa. Okay, so now, so we got what all things we want. We got this sign number. This sign number is 0. We got it. Exponent value we got it here. Okay, and mantissa value we got. Now all together we need to represent that in IEEE 754 double precision format. Okay, how to represent that in IEEE 754 double precision format? If you want to represent that, we need to have a 64-bit length. Okay, this is 64-bit length. Let's say for example, let me correct this. Okay, so 64-bit. Let us think that it's 64-bit now. So here we have the sign bit, and here we have the exponent part, and here we have the mantissa part. So sign bit is 0. We already know that. So sign bit we are represented as 0. Okay, so sign bit is 0. And exponent part what we got? Exponent part what we got is this one. Which one? This corresponding number here. All together what we have taken here, right? So this number. So can I copy this? Yes, copy this. So it's 1 0 0 0. So it's like 1 2 3 4 1 2 3 4, like that. You can copy 4 digits, then 1 2 3 4 digits again, 1 0 1. Altogether 4 plus 4 8 9 10 11. So this is 11 bit. Correctly it is there. If you got less than that, you can push the number of zeros that side. Okay, so in double precision format, what we know, it is 64 bit we know. So altogether this length of this is 64 bit. Okay, out of the 64 bit number in double precision, so 1 bit will go for the sign bit and 11 bit will go for exponent. So 11 plus 1 12, and remaining bits will go for the mantissa part. How many number of bits for the mantissa part? It is 52 bits. So this mantissa will be 52 bits. So how many bits we got? The value, what value we got here? Value what we got here is 0, 1, 0, 1, 0, 1, 0, 0, 1. Where we have got this number from? We got this number from this normalization 0, 1, 0, 1, 0, 1, 0, 0, 1. Okay, so this corresponding part we are taking it. Okay, so count how many are there: 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so remaining all the values are zeros. So we need to represent technically 52 number of bits here, and that 9 already we represented. So remaining all the bits are zeros. So this way, if you represent, we can able to say that that corresponding number is converted into its double precision format. Okay, so simple. You can please try for different numbers. You take different numbers of your choice and try to represent them by using single precision and double precision. All right. Thank you.